Today I would like to explain about EFA, which is Common Collector Amplifier with emitter follower, and this is our group mate. First, I would like to talk about our objective in this experiment. We would like to measure the input and output impedance of the Common Collector Amplifier. Second, to measure the power gain of the Common Collector Amplifier. Third one, to study the phase relationship between the input and output signal of the Common Collector Amplifier. For this experiment, the equipment are needed is 12 DC power supply, dual channel oscilloscope, a digital multimeter, function generator, project board with connecting wires, 390 kilo ohm resistor and 10 kilo ohm resistor. Also, we need a potentiometer of 1 kilo ohm, 10 μF capacitor and 47 μF capacitor with transistor PC108. This is the circuit diagram that we need to set up. And this is the real setup based on that circuit diagram. For procedure in part 1, this is we do the DC analysis, calculating and measuring the DC operating voltage found in a common collector circuit. First, the circuit is connected as shown in figure 1. We nak connect potentiometer R. For now, the DC collector supply voltage, which is VCC, is adjusted to 24 DC. The AC input voltage should be turned off. The DC voltage between the base of Q1 and ground is measured. Next, the DC voltage between the emitter of Q1 and ground is measured. The emitter current is calculated. Next, the DC voltage between the collector of Q1 and ground is measured. And we need to find the collector to emitter voltage, which is VCE, is calculated. Last, for the measurement and calculation in step 2 to 5 are filled in the table 1. For the calculation part, to find the IE, we need to divide the VE over RE, and we got the answer 1.14 milliampere. For VCE, we need to deduct VC minus VE, and we got the answer of 12.62 volt. Next is part 2, which is DC analysis, voltage gain, and input impedance of the DC amplifier. The signal generator is set to the sine wave function at a frequency of 1 kHz. The amplitude of the function generator was increased slowly until the output voltage, Vout, is about 150 mV peak to peak. Do not change the setting until the completing the experiment. The input voltage, which is Vin, is measured. The value was recorded in table 1. The voltage gain, AV, is calculated by dividing Vout over Vin. The input impedance, which is Zin, was calculated. Input current is calculated by dividing the Vin over Rin. Input power is calculated by dividing the V square in over Zin. DC load line analysis graph is drawn for a common collector configuration and determine the Q point transistor operation. On the same graph, Vin and Vout wave signal and their amplitude is sketched based on the experiment setting.
Parts. Using the formula that I given before, we can calculate the AV, which is the 0.977, almost to 1. Since beta for transistor BC108 is the range of 110 to 800, so I take the we can assume the beta is 110, and we insert into the Rin formula, and we get the Rin value is 195 ohm. Next is find the In using the Vin divided by Rin, and we get the value of 0.276 milliampere. And lastly, for the Pin, using the formula Vin square over Rin, we get the power in equal to 1.49 multiplied by 10 power of -5 watt. This graph illustrates the DC load line analysis for transistors in circuit. To achieve maximum efficiency and signal swing without distortion, we ideally place the Q point at the center of the load line. As shown in the calculation, we set the collector voltage, which is VC, to the half of the supply voltage, approximately 12 volt. By projecting this point into our graph, we determine the corresponding collector current, which is IC, is 1.25 milliamp. For the next part is part 3, which is the output impedance of the CC amplifier. Firstly, R4 is inserted back to the circuit, and the potentiometer being adjusted until Vout is half of the value obtained in part 2. After that, return VCC to 0, and without disturbing the setting of R4, R4 is removed from the circuit and measure its resistance using digital multimeter. The value of R4 is equal to the output impedance Rout of the amplifier. Next, the output power, which is Pout, is equal to Vout square over R is calculated. This is the calculation to get the Pout. Firstly, the value of Vout, which is the 52.67 millivolt square, and divided by the Rout, which is the RL, 24.6 ohm, and the answer is 0.1127 milliwatt. Next is part 4, power gain, which is the power gain of the CC amplifier. The power gain is calculated and recorded according to the equation below, which is AP equal to P out divided by P in, which is the P out value is 0.112 milli divided by 1.49 multiplied by 10 power of negative 5. Then the final answer is 7.517. For the last part is the part 5, which is the phase relationship between the input and output signal of the CC amplifier. Firstly, both channels use the oscilloscope to display the input and the output signal of the CC amplifier. Next, the actual waveform image is captured and saved to our own thumb drive. And next, the phase difference of the two signals is determined. From both of this picture, you can see that the waveform is actually equal. So there is no phase difference between them. For the quiz question, there is 5 quiz. Firstly, the common collector circuit is used mainly as an impedance matching circuit. Next, the input SC signal is applied between the base and the ground. Next is the SC voltage gain is less than unity. Next, the output impedance is low. And lastly, why the common collector circuit also called the voltage follower? It is called a voltage follower because the output track, the input phase and the magnitude gain almost to 1 and minus a small 0.7 voltage base emitter drop. Now we enter the discussion part about the common collector amplifier, or what we more commonly know as emitter follower. In part 1, we focus on the DC setup. Essentially, we are making sure the transistor was awake and ready to work. By checking the voltage, we saw a classic drop of 0.6 volt between the base and the emitter. With our VCE setting at 12.62 volt, we confirm the circuit was perfectly biased in the active region, meaning it's stable and ready for a signal. Moving to part 2, we look at how it's actually handled the AC signal. The big takeaway here is the voltage gain, which come at 0.977. That's exactly what you want to see in an emitter follower. Again, that not just shy of 1, meaning the output is following the input almost perfectly. We also plot the input impedance at 195 ohm. Moving into part 3, we measure the output impedance using the voltage divider method and found it to be very low at just 24.6 ohm. This low impedance is exactly why this circuit is so good at driving heavy loads without the signal dropping off. Even though we are not seeing a big jump in voltage, part 4 show us a significant power gain of 7.517. This is happened because the circuit provide a major boost in current, ensuring the load get the power it needs. Finally, in the part 5, the oscilloscope confirmed that the input and output signal are in phase, with a phase shift of approximately 0 degree. In short, this 5 part proves that the CC amplifier is an ideal tool for impedance matching, offering high current and power gain while keeping the signal perfectly aligned.
In conclusion, this experiment provided a clear understanding of the operation and practical usefulness of the common collector CC amplifier. The results showed that the CC amplifier has high input impedance and a low output impedance, making it effectiveness for impedance matching and for driving loads efficiently. The input and output signals were also observed to remain in phase, confirming the emitter follower behavior of the circuit. Although minor errors may have occurred due to the measurement limitation tolerance, the experimental result closely agreed with the theoretical expectation. Overall, this experiment demonstrates why the CC amplifier is widely used in electronic circuit for buffering and power amplification application. And this is the reference we use for this experiment.